I'm a junior studying material science engineering, and my final project for Engineering 105 is identifying mirror and glide symmetry in an image. I'm very excited to take you through my project. So let's begin by defining mirror symmetry and mirror lines. Mirror symmetry is a symmetry with respect to reflection, where a figure is indistinguishable from its reflected image. Mirror lines produce another object on opposite sides at equal distance but opposite-handedness. In the context of our algorithm, the nth mirror line is detected if n minus k rows or columns, depending on whether it's a vertical or horizontal mirror line, and n plus 1 plus k rows or columns have identical pixel values, where k ranges from 1 to mirror size, with each being an integer value, considering that it represents the index of the row or column, which has to be a positive number. Examples of mirror symmetry are several. For instance, in nature itself, we see a lot of mirror symmetry. This image of a crab, there's clearly a vertical mirror line going through the body of it. We also find a mirror symmetry in mathematical functions and transformations. For instance, this bell curve has a mirror symmetry at mu, and other examples of mirror symmetry are presented in the corner, top right corner. We can also see that diagonal mirrors may exist. However, for this project, we just looked at rows and columns. So what is glide symmetry and what are glide lines? Glide symmetry is a compound symmetry operation combining a reflection and a translation by a fixed value, usually denoted by the Greek letter tau. Translational vectors are oriented parallel to the mirror line. The standard notation for glide lines is a dashed line, while for mirror lines it's a solid line. In the context of our algorithm, the nth glide line is detected if n minus k rows or columns and n plus 1 plus k rows or columns contain identical pixel values that are translated by a constant value, where again k ranges from 1 to the size of the glide. Examples of glide symmetry include in molecular packing and crystal structure, and also interestingly in music. This musical composition was found to have a glide symmetry within it. So what is the goal of this project? Identifying localized mirrors and glides, and there's an emphasis on localized here because in reality, an image may only have up to 4 absolute global mirror lines, where due to the fact that mirror lines are supposed to divide the image into regions of equal area, and that would be through the center, vertically, horizontally, and through the diagonals. However, I wanted to look at a more nuanced view where we can even see localized mirrors and glide lines. And the way this is done is that it actually inputs users' choices of parameters like size, which is the extent to which the mirror and glide symmetry holds, and a tolerance value to even allow for imperfect mirrors. Ideally, I would like my project to create output images that are presented below. So the first image, we see a picture of a city which clearly has a vertical mirror line running through the center of it. And then we see this pattern where there are multiple vertical and horizontal mirror and glide lines. So how does this algorithm for mirror and glide line identification actually work? Before I get into that and show some of the code, let me just mention the few key features of the code. Intense algorithm development, image analysis, as the input image was converted from RGB values to grayscale, and then graphics generation to actually draw the mirror and glide lines on top of the original image. Limited user interface, in the sense that users were prompted to add their own input values and were even advised what the limits of these values might be. And independent learning that came out of this project, which was not taught in lectures or in any of the homework assignments, was the use of a map, which is a higher order function. I used the map to efficiently identify glide symmetry and match multiple glide lines to a single translation value. So let me just show you all how this code actually works. So let me, as you can see, there is this user interface where it asked for a file name with the correct extension, which must be in JPEG or PNG and within single inverted commas. So I've used an image already inputted, white blank.jpg, which is essentially, as the name suggests, just a blank white image with just a background of white background with nothing in it, just to show how these key, it's the most ideal version where we can see this code is doing something correct for us or not. The next prompt, which I'm yet to input, is select a minimum number of rows or columns for which the glide line is valid up to a limit of 205. So the number 205 is very specific. It actually relates to the dimensions of the image we inputted. So as we can see from code lines 10 through 21, the size, the dimensions are determined, and the smaller of the two are found. And based on that, we can set a limit of how big the glide or mirror could be. So let's put in a value of 10. And there's also this note, which is quite important, that a glide size of greater than 10 takes considerable runtime. So let's stick to a value of 2. The next prompt for the user is select a minimum number of rows or columns for which the mirror line is valid. Again, up to 205. We could go a little higher in this parameter, and let's say 50. Select a tolerance to allow deviations from a perfect mirror. Let's take the case of just perfect mirrors where we allow no deviation at all, because this is a pretty clean image. And then we are ready to run our code. As you can see in this output image, which I'll just zoom into, we can see a solid mirror lines as well as glide lines running through the center. There is a small deviation from these, but this has got to do with the glide size that we put in and the initial parameters. And we can see that the glides, vertical and horizontal glides, as well as the mirrors, are pretty accurate. What's that our code produced? As we see for the white blank JPEG, we have pretty accurate glide and mirror lines going through the center of the image, both vertical and horizontal, which is a good example of how our code works very well. However, for the square JPEG, we first see that when mirror size is large and mirror tolerance is set to 0, essentially meaning only perfect mirrors can be identified, we do not see any mirror lines going through the square in the center of the image. However, when we increased mirror tolerance to a high value of 10,000 and decreased mirror size to 50, we do see these solid lines appear, the mirror lines appear through the square vertically and horizontally. However, we also see this kind of ghost line, which I discussed later, going through the side of the square, and this is an example of an inaccuracy in our output. Lastly, for the cow JPEG, we see some mirror lines that should be present not being there at all, which is another example of perhaps inaccurate imperfect images not being able to produce mirror lines as our naked eye would expect it to. Because this image was made manually, perhaps a small shift in each cow didn't allow them for a mirror line to go through. And we also see some glide lines which aren't perfect. So some successes, challenges, and recommendations, as well as different approaches to solve the same problem. Some of the challenges that were actually successfully overcome were decomposing multiple successive mirror lines into a single line. Initially, when this piece of code did not exist, there were huge blocks of consecutive mirror lines and glide lines which just covered like all the white space of the image essentially, and kind of defeated the purpose of this algorithm. Therefore, creating this code which detected successive mirror or glide lines, and then position them in the average of all those values, essentially decomposing them to a single line. Another success was creating a map data structure for identifying glide symmetry, where a constant glide value was detected, and then a glide line could be extended beyond just 2 columns or rows. So glide size could be take larger values. The use of mirror tolerance, as I mentioned before, allowed for imperfect mirrors and improved visualization, as we saw for the square image. And lastly, resolving scenarios where there were equivalent mirror and glide lines. Oftentimes glide lines can also be mirrors. However, mirrors are considered to have proper symmetry, while glide lines are improper. Therefore, I decided to give preference to mirror lines, and whenever there was a conflict on an exact same position, I created code which gave priority to the mirror line. Some challenges and inaccuracies in the results. Finding perfect images containing symmetry elements was definitely a big challenge, because no image had pixel values that actually mirrored or were glides. Oftentimes, the only really accurate mirror and glide lines I found were ones in blank space, which makes sense because they had a constant 0 value in their pixels. Another challenge was when glide size exceeded 10, the runtime was very long for the get glide line function, and this hampers good visualization, which would otherwise be possible for bigger glide sizes. Then another thing which I showed through the outputs that the code produced, there was a lot of ghost lines which were blatantly wrong visually, and this again could be just perhaps a function of image quality and the inability of our code to work on real images. Other potential approaches and recommendations for this coding assignment could be machine learning models using a rich data bank, using RGB values instead of grayscale, where there could be greater perfection found because by virtue of having 3 like red, green, and blue values as opposed to just a single value. And then finally, allowing for diagonally oriented mirror and glide lines which exist. However, our code only looked at vertical and horizontal ones. Thank you so much for listening.